This is a really interesting topic, points of concurrency in triangles. So again, we're going to be adding to what we understand about triangles, and I promise you that there is more going on than you expect. So there are four that we're going to learn about, 4 points of concurrency, but there are many, many more, and I can show you a list sometime if you're interested. I think that there are, probably 30 or 40 or maybe even 50 different points of concurrency in triangles. We're only going to learn the 4 of the most basic ones. So a point of concurrency, I like to think of it as the word as con and cur. So like the word occur, so it's almost like con occurring, and con means together. So concurring means that it's happening together. So concurrency is when you have points that happen together, or in other words, when you have things that are intersecting. Like if I had this line, oh, that doesn't work very well. Green on green does not work well. If I had this line and this line and this line, that point right there where they all come together, that's the point of concurrency, because it happens on this line, and it happens on this line, and it happens on this line. It happens on all 3 lines, so that point right there is the point of concurrency for those 3 lines. So happening together. The orthocenter of a triangle is where the altitudes meet. So of course you have 3 sides and 3 angles of a triangle, and so that's what we're going to be basing all this on. So when you have 3 altitudes that meet, that's the orthocenter. If the triangle is obtuse, this will be on the outside of the triangle. If the triangle is acute, it will be on the inside of the triangle. So that, that looks like this. Credit to, I pulled some really awesome images from Valerie Russell at the University of Georgia. So let me just zoom in on this real quick. The orthocenter of an obtuse triangle is outside. So here's the orthocenter out here. Again, the orthocenter is from the altitudes, right? The altitudes. So if we draw an altitude from this side, it goes through the triangle, but notice that the altitudes from the other 2 sides are running outside of the triangle themselves, because the triangle is obtuse. And so remember that an altitude is where you have any triangle here, and you want to try to draw a line from a vertex and drop it down so that it's perpendicular to the opposite side there. So that works well. You can think of it back in the day when you were doing basic geometry, that it is the height of a triangle, measuring the height of a triangle. So you always have to measure a height perpendicularly. And so if you had something like this, you're going to be able to draw one there. But how do I draw an altitude from this point over here? Well, I can't go through the triangle because I'm way out here, stuck out here somewhere. So my altitude ends up being right there, even though it's not inside the triangle. That's what it is. So when you have an obtuse triangle, 2 out of your 3 altitudes are going to end up running outside of the triangle. So the orthocenter can indeed be outside of the triangle, which is counterintuitive because it has the word center, right? The orthocenter, but it's not really a center if it's outside, is it? Well, it is a center because we're calling it a center based on this definition. If it's a right triangle, the orthocenter is going to be right on the vertex across from the vertex that's the 90-degree angle. Just like this, if you notice here, the orthocenter was outside, going this way. It was outside of this obtuse angle right there. So the orthocenter is directly related to the position of the defining angle. So for an obtuse, of course, you can only have one obtuse angle, so it's going to be beyond the obtuse. it's kind of shrunk back in here. Notice it was out here and it's kind of shrunk back in a little bit. So for a right triangle, the orthocenter is right on that 90-degree angle. And for an acute triangle, everything is playing business as usual, as you would expect, and so it has shrunk all the way back inside the triangle because all of the angles are nice and acute. So that is an orthocenter. Let's move on to a circumcenter. A circumcenter is where all the perpendicular bisectors meet. So perpendicular bisector means that it is bisecting the side into two congruent parts, and perpendicular means it's 90 degrees from it. Also, this is the center of a circle that is circumscribed around the triangle. So if you have a triangle, it's a circle that goes all the way around it like that. Circumscribed, just like you're circumventing, you're going around something, or circumnavigating the globe means you're navigating around the globe. The circle that passes through all the vertices of a triangle. So notice that wherever this circle is, the center of the circle is the circumcenter. But if that's the center of the circle and the circle goes through all three vertices, that means that the circumcenter is equidistant from all three vertices. That's important to note, okay? Because they would all be radii, right? It would all be radii. Now the incenter, or excuse me, wait a minute. I have a picture for the circumcenter. The circumcenter looks like this. So again, this comes from Valerie Russell at UGA. And the circumcenter here, perpendicular bisectors, can be out because there's an obtuse angle right there, right? There's an obtuse angle. It's throwing everything off. The perpendicular bisectors are shooting way up here, but that's the circumcenter. And notice that since all three vertices are on this circle, then the circumcenter is indeed equidistant from all three of the vertices of the triangle, because it's all just on this circle that's going around, right? When it's a 90 degree, a right triangle, the circumcenter is right on the hypotenuse. But again, you can see that it splits this, so this would be a radius, this would be a radius, this would be a radius. It's equidistant from all three vertices because they're all radii. So for an acute triangle, it's smack in the middle. Or not smack in the middle, but it's inside the triangle because everything is collapsing in towards the middle here. Okay? Next up is the incenter. The incenter is equidistant from all three sides, okay? Because we are using this, we're constructing angle bisectors for this one. Angle bisectors are always equidistant, so if you have an angle and you bisect it, each of these points along here is equidistant from the points along here and the points along here, because I've bisected it, right? So these are the same. So they're the same distance. If you measure across here and here, they're going to be the same for all the points. So it's equidistant from all three sides, and this is always found on the inside of a triangle. All right, because this incenter is actually the center of the circle that is inscribed in the triangle. So if you're thinking about inscribed circles, they're always the whole circle has to be inside the triangle, right? It has to be inside here. So if the circle is always inside, then the center of that circle is definitely always going to be inside the triangle. And lastly, we have centroid, which is where the medians meet. This is always found on the inside of the triangle also, because it's only a product of measuring two midpoints. And this is also can be thought of as the center of gravity. You basically are taking this excuse me, I need to get some sleep. So you're going from a vertex to the midpoint of the opposite side, and since that is only ever going to be leaving you inside the triangle, then the centroid has to be inside the triangle. You can also think of this as a center of gravity because you're looking at the halfway points of each of your sides, and you're essentially your massing of the triangle. So this is almost like the center of gravity of the triangle's mass, if you want to think of it that way. So the interesting thing about the centroid is that it splits these medians into 1/3 and 2/3 parts. So, for example, going A to O is 2/3 of A to E. So A to O is twice as long as O to E. So this would be 2/3, and this would be 1/3 of the whole median. And just like here, this would be 1/3, and this would be 2/3 of that whole median going from C to D. And this would be 2/3, and this would be 1/3 of that whole median going from B to F. That always happens for every centroid. Okay. So I'm going to. You're probably going, oh my gosh, I'm never going to keep this straight. There's so many words and bisectors and what kind of whatever. So let's go through and actually informally construct one of each. Okay. We'll start with the altitudes. Okay, so we're going to start with the orthocenter. So this is going to be orthocenter. That's going to be orthocenter. And this is the altitudes. Orthocenter's altitudes. So coming from this point, and I'm dropping a 90-degree angle from that point down to there. It looks like it's about there. And I'm just sketching this, so this is not going to be exact by any means. And so here we're going from the point B down. It's going to be somewhere over in here. Of course, I only really have to do 2 of them because I know that they're going to intersect at the same place, but I'll do all 3 just to prove it to you. So here's the 3rd one, and look at that. If it isn't happening, it's right there. They all 3 intersect. So that would be the orthocenter. Next one we're going to do is the medians, which form the centroid. Okay. And so this is just going to be a matter of finding midpoints. So here this is 5. So 2.5 is going to put me there, so that those are congruent to those. And then over here, that's 10. So 5 is going to put me here, so that that is congruent to that. And then down here, this is 10. So 5 is going to put me there. Alright, so that is congruent to that, and so now I just go through and I connect all the sides. So here, or connect all the medians. So then there, and that, and of course I really only need to get 2 of them, because I know that the 3rd one, look how beautiful that is. Whoops, look how beautiful that is. I know the 3rd one is going to be right on there also, so I don't really need to do all 3, but I'm going to do it for the sake of the learning. Next, we're going to look at angle bisectors, which gives you an incenter. Okay, and so looking at angle bisectors, I'm just sketching this. Okay, so it looks like the angle bisector here is going to do something like this, and the angle bisector here is going to do something like this. And the angle bisector here is going to do something like that. So again, there's that, and what I'm doing here is I'm splitting these so that that is congruent to that, and that is congruent to that, and that is congruent to that. Okay, so there's your incenter. And lastly, the circumcenter. Which are, of course, the perpendicular bisectors. So we need to find the midpoint. We need to find the midpoint of each side. And here. And here. Okay. And instead of just going from the vertex to the midpoint, which would have been the median, we are going to bisect these perpendicularly. So there's one, so that's a right angle. And here is one, so that's a right angle. And here is one. And look at how, I mean, it's almost like predictable at this point, right? There's one right there, and there's my circumcenter. And notice that the circumcenter is equidistant from all of the vertices. Now, it just happens to be, this has happened, it's just coincidence, that this perpendicular bisector also comes over and meets with vertex C. That is completely coincidental. I did not do that on purpose, and it has no actual meaning or bearing on the circumcenter at all. So you're probably going, well, this is just a lot of tedious crap, and I don't want to have to remember all this. Well, lucky for you, there is an acronym, or a little saying, I guess not an acronym, that'll help you remember this. All of my children are bringing in peanut butter cookies. I love peanut butter cookies. And this is the way that I remember this. So, all of my children are bringing in peanut butter cookies. All right? All of, meaning altitude, orthocenter. My children, meaning medians and centroid, are bringing in angle bisectors, incenter. And peanut butter cookies is, of course, perpendicular bisectors, circumcenter.